start by thanking you, Emma, for giving us this talk today at the CDY-Initiative. Emma is well known in this field, a long history in atmospheric Cherenkov telescopes, in galactic sources, in working with H.E.S., as well as in magic. Currently, you just started at DESY Zeuthen, I think, recently.
Right.
But before that, first of all, your PhD was in the optimization of the magic telescopes for pulsar observations, and you did this with Oki Dieger in the Potchefstroom campus in South Africa. And then there was a postdoctoral degree. You were in Barcelona, you were in Madrid, Complutense in Madrid. You were the Ramon Fellow in Barcelona, research postdoctoral fellow at NPIK, and experience in H.E.S. as well as in magic, and then also in CTA, where you were the co-science working group lead for CTA. And your expertise has been in pulsars, in pulsar halos, in galactic sources, observation of H.E.S., extensive experience in binary systems, as well as working with BLAT, as well in magic and H.E.S. So let's get started. Thank you again for giving us this talk. And you will speak on recent results from H.E.S. observations of the Galactic Plane.
Yeah, thanks, Resmi. And thanks a lot to the organizer for inviting me to give this lecture. And I hope I convince you that H.E.S. is still like a top instrument. And it's not like some people think this Cherenkov field is kind of saturating before CTA, but actually we have a very, very good and advanced instrument with many hardware and software improvement. And I'd like to tell you a bit on the latest results we get with H.E.S. And for that, first, I'd like to say a couple of words, remind you how is the Imaging Atmospheric Cherenkov Telescope Array technique is. And I just want to put a point on the strength and the weakness of these telescopes or these telescope arrays, especially comparing with the new results that we're seeing from particle detectors like LASSO that we had two weeks ago, or satellites like from like LAT or Agile. And then I will discuss kind of some of the new results which are related to the galactic science we're doing right now, not just discovering new TeV classes of sources, but also what we're doing right now is revisiting some of the brightest sources with the better sensitivity and better analysis technique, and getting more advanced results. And in the end, but last part, I just want to say a couple of things on the general galactic population, especially Pulsar nebulae and Supernova Remnants, which is, you know, the most populated source type in the galaxy, and also mention a couple of new source classes that we have been observed in and they've been detected in the last year. So this is the very well-known plot in which we've displayed the sensitivity of different instruments with respect to energy in range in which they work. And you've seen these plots very often. And here the gray is just the crab, it's just marking the crab flux. This is one crab and it goes down in tenths, just to show this, the typical sensitivity that we are talking about. In the most left part of the spectrum, this is where we have the satellites working. Right now we have, as you know, Magic, LAT and Agile, and they are characterized for having they work in a survey mode with a large study cycles, are basically all the time observing the sky. And they have a kind of good PSF in the GeV range. And as you go down to the MEV regime, then it worsens up to 3 degrees. I mean, you go to the highest energy with said before, we heard about the new results coming from particle detectors like the Hoax, water detectors, Cherenkov telescope like Hoax or LASSO. In this wise, they work mostly above 10 TeV up to more than PeV. And this is a very good instrument to get unbiased surveys and unbiased surveys of the galaxy or catalogs, because they're always observing, they don't have any limitation basically, and the duty cycle is very large too. And they have this large aperture. And then here in the middle, we have what we call it the Imagine IACT, the Imagine Array Cherenkov Telescope, which is basically MAGIC, H.E.S.S, and Veritas. And this is the line for CTA, in which we'll be working. We're working right now, and will be operating in a couple of years. So the good thing about these instruments, or the bit good or bad, depends on the science you want to do, is they are pointing instruments. So that means the field of view is kind of limited. And if you want to get the aperture, it's of the order of 0.003 stereo-radians when you compare to these other instruments. But on the other side, we have a very good PSA for angular resolution of the order of 0.05 or less if you have the right technique. And something else that is also limiting our observation is that we only can observe when in dark conditions or moderated light. That means basically for a year, if you want, you can get 1,500 hours of observation time, and that actually limited our observation power, let's say. So basically, this you all probably know very well what is the principle of the Cherenkov technique. You have a primary particle coming in the atmosphere, and then this primary interacts with some nucleus here or magnetic field, producing charged particles, and these charged particles, when they travel faster than the speed of light in the medium, they produce a flash, a very fast flash of Cherenkov light, and then this goes onto the ground with a very large cycle of, we have a cone of light going around like 100 meters or so, depending on the energy of the shower. You have some telescope there, you can reconstruct, basically there's a cone you cut and you reconstruct this kind of ellipse, and then you can combine the images of the two and then get an information about the primary particles. And basically, well, that's some of the images we took with CTA, with CDHY, which is the large telescope. This is per gamma ray-like event, and this here you see the typical hadron-like event in which you have this kind of ring which belongs to muons, and then some kind of very complex shape light, which is related to this kind of more complicated shower. So basically, by looking at the shape of these showers, we can distinguish very nicely the gamma rays or the photon-induced shower from the overwhelming cosmic ray background. By looking at the axis or where the direction of the arrival direction in the camera, we can say things about the arrival direction, and then the angular resolution. And then from the size, we say like the amount of light we get, then we get a very good estimation in first order of the image resolution. So this is the very basic thing, and then I applied here to H.E.S.S. H.E.S.S is a system of 5 Cherenkov telescopes. These 4 they are located in a square of site 120 meters, and then they were operating from 2003 to 2012. And they have been upgraded, the cameras have been upgraded later on in 2017, and now they are really working with a very good sensitivity. And then in 2012, this large telescope we call CDHY was installed in the center of the array, and then they could decrease the energy threshold down to 30 GeV. And then when you do in hybrid mode, then you have something like 80 GeV. And these guys alone, you can go up to 100 GeV. So basically, Something else I'd like to add is last year, we also put one of the CTA cameras in CDY. So now CDY is really getting very, very good sensitivity as well. So one of the good things also from H.E.S. is that it's in Namibia, which is a very good location for Cherenkov astronomy. And also it's a very good location to look at the galactic plane because it's in the southern hemisphere. Basically, it's the only Cherenkov instrument which is in the southern hemisphere. So we have like unique vision of the galactic plane. And this is what here. This is a galactocentric plot in which the sun is here or H.E.S. is here. This is what we actually see, and this is some of the sources we have detected. And then here you have some limits for luminosity. Here, that would be 10 to the 34x per sec, and that would be the horizon for 10 to the 33. And then you see that we see very kind of deep in the galaxy, and we cross several of the arms. Of course, we still have a lot of problems, and whenever we look into the center of the galaxy, then we start crossing many arms. Then sources start piling up. And this is here you see the region that we have been looking at. The main GPS the Galactic Plane Survey was done from 2003 to 2012. And this is this region over here. This is overlaid on this blank CO data. And there's several other surveys. This is IGRA, this is IGRA in orange. And this is the Veritas one. And so just a comparison. And here is the H.E.S. one. And one of the things we tried to do before we publish all this data was to get a kind of uniform exposure, to get at least down to 1% in mostly all the parts in this galaxy, from 80 degrees in longitude down to 240 in India. So some of the things that makes H.E.S. very good instrument to do this kind of surveys is first, besides being in the south, is that we have a very large camera. The camera of H.E.S., the cameras are around 5 degrees. That means up to 3 degrees you have a flat response of your camera. So that means you can look at a very large region of the sky with very good PS angular resolution and energy resolution. So that's important when you have a large number of extended sources, especially in the inner part of the galaxy, and also when you have a lot of diffuse emissions stemming from active regions, like we see in the galactic center. This is, for instance, an extract of the GPS around the 18 right ascension. And then you see here, there are many extended sources with very complex morphology. Some of them are point-like. And then for this, you really need to have a good understanding on the background, on the acceptance of your instrument. And for that, we have chosen a pointing scheme that basically maximizes the sky coverage, minimizing the acceptance variation. And so we had these 2 rows of pointing, and this is what we've been using for getting the whole GPS data. And we also have a good angular resolution, and this is also very important. Just to convince you that how relevant is this, I just make a little game, a little toy, which is basically I simulate a shell-like source with a radius of 0.7 and a width of the shell of 0.1. And this is what H.E.S. could see with some kind of shell-like morphology like this one, which could be 1713 or any other like this. And as soon as you go at worst PSF, like 0.2 degree into Gaussian angular resolution, or even 0.3, then this shell-like morphology, you basically lose all the information about that. Of course, this is very rough, and you can improve these things. But just to give you a taste of how important it is to get this very good angular resolution. This is again some toy model for 2 nearby sources. This is nearby the center 0.7 degrees, almost 1 degree apart, and they have a size of 0.2. This is something very typical that we see in the GPS with H.E.S. convolving this model with H.E.S, you will see something like this, two separate sources. And again, as soon as you go down to 0.2, 0.3, then what you get is a very blurry image of two sources that become like a big blur here. So this is something that we should take into account when we look at the GPS, especially, as I said, because in the center of the galaxy, there is a lot of sources one on top of each other. Energy solution is also a very important thing. It's not like super basic, but it's also a combination with the angular resolution makes it very important, especially when you look at resolving sources and confusion of them. This is another just example. This is a MOOC source. That would be what you see with H.E.S. And then as you go down to 60% to worsen your energy solution, then you will see changes in the slope, like really, really large. In a way you couldn't trust it, something like this 1.5, but then you'll see something like 2. So this is something that that we should take into account when we look at this data. And I just want to move to the data we observed. This is the Galactic Plane survey image that you all probably know. We publish all this data, which amounts to 2,700 hours. You can find all the information of this data in this web page, and then we provided flux maps, significance map, and even code software that you can use to look at all these sources that appear. As you all know, in the center it's very populated, and then as you go into the side, the number of sources seems to decrease, and it's just because the gas is basically decreasing and you process less arms. I just want to also say that for some of the regions, we have new data with this improved array that I thought with the new cameras, CD5, and they are ranging up to 3 times, tripling the observation time that we published. So this is again the one published, but now in many of these sources that they had interesting features, we reobserved. Now we are looking at these things in details. So beside that, we also improve our reconstruction technique. Now we, as you probably know, Gamma Pi is one of the tools, open tools for CTA. Now it's one of the H.E.S official tools, and this is basically using a 3D technique in the sense that you feed everything together, the energy, the morphology of the source and the spectrum. So you benefit of having the information of all the photons, not just in beams and making maps, but just having the whole thing, a bit a la LAT, if you want to. So using these things and using this kind of technique, for instance, we revisited this guy 1702. This is one of the first sources that is by H.E.S, and it's a very bright source. Now this is what we saw is a different energy bands. Then we see a very different morphology. This is above 2 TeV, and then you go here on increasing the energy until you have up to the 40 TeV. And this, we actually saw that this is very well explained, just not by one source, but 2 sources. You have a point-like source here, and this kind of a much more extended halo-like source around it. We don't know yet if they are correlated or not. It could be that by chance when they are one on top of each other, although we don't see any discontinuity between the two. And something also very, very interesting that we see is that we can distinguish very nicely the spectrum, or measure the spectrum of the two components right now. The one is very, very soft, one very soft, it's around 2.6, and the other one, the small one, has a spectrum of 1.5, and it extends, this is for 2 TeV, and it extends up to 100, a bit more than 100 TeV, with a spectral index of 1.5. So we looked at it. You can find more details in this publication of this year. If hadronic, then first you need to explain how you get this very hard spectrum, 1.5, but then that would imply a cutoff in the spectrum of the particle of more than more than 800 TeV or 0.8 PeV. Of course, this cutoff in the particles is relaxed if you play a bit with the spectral index, but it's always more than 550 TeV. And energetics, we also calculate energetics. Something that we also see in the morphology is that there is no like a very obvious counterpart. There's no pulsar here. There is no, well, or just a deposition of this very hard source, just an X-ray source, and there is no like a very obvious cloud connection. We can also play with considering the leptonic emission. Then again, you have to find this 1.5 spectral index and trying to see how you reconcile this with the spectral, an electron spectrum of basically 1. And then again, the energetics you need in the case of electrons is pretty high. So this is one of the nice results we get with this kind of improved gamma hadron reconstruction. And something else that we're trying to do now is to try to improve our analysis for large field of view sources. So basically, before that, we used we always estimate the background in our maps by methods based on what we call the ring background maker or the ring background. And then what you have is for each position of the map, you just evaluate the background in a ring around this position. In many cases, when you have exclusion region, because you don't want to use a region with another source to evaluate your background, then often this ring is just limited to some part of the camera. And whenever you have a lot of sources or a lot of diffuse emission, that becomes really difficult because you cannot evaluate the background because there's basically nothing left in the camera. So now what we're trying to use, and we've been testing heavily, is what it's called field of view background. And in that case, what you use is you use the whole field of view, and then you use tabulated tables using extragalactic field of view for different zenith angles, and then we apply for each run of each 25 each chunk of data separately to fit it with the galactic observations, assuming a radial asymmetry. And then what we did with that is we actually tested a lot, and it is performing pretty well, or at least we get very compatible results when we get with the traditional background techniques. And then now that we can look at larger source, we try to first compare with other surveys. This is something again that we did in collaboration with the Hoax collaboration. This is the Hoax, as you know, is also surveying the part of the galaxy. This is the visibility of Hoax. So we compare this region here, which is basically this map here, with the one that is the one that we're looking at, and we have this overlapping part survey that we can compare to each other. And this is what we see when we compare. Again, details of this analysis and results can be found in this publication. This is what Hoax is using their own reconstruction technique, and this is what we see. This is for SkyMap, integrating for a radius of 0.1 correlation radius using this green background maker. But then again, we did the same game, but using this field of view background maker over here, and using a correlation radius in our maps of 0.4. And as you can see, this is again Hoax on the top and H.E.S on the bottom. And we see a very good correlation. Basically, we're looking at the same energy, which is reassuring, but not straightforward. We see the same information from the two guys. And what is clear is that Hoax is integrating for more diffuse emission than we are. And that explains somehow why sometimes we have a lower spectral flux compared to Hoax. And this is once we understand all these differences, then we can actually use Hoax and compare the two things one by one to also trust some of the diffuse emission we saw before. This is, for instance, what we saw, this is the region of 1930 that we detected a while ago, and now we compare it to Hoax, that they saw this source here, 1928 plus 178, and then we indeed see some emission coming from the same region, which is probably associated to pulsar with nebulae to the sky, 1928, which is the typical pulsar or bright E dot pulsar with the middle age. Another comparison is, of course, 1908. 1908, for all of you, they probably remember, is one of these first sources detected by Milagro, and then it was seen by H.E.S. and by Veritas, and now we have a nice spectrum by Hoax and LASSO too. Is this big guy with almost 0.81 degree, and then there is some emission coming here, which is this is defined. This was called by Hoax 1906 plus 085. But when we look at our map using this field of view 3D technique, we indeed see this kind of diffuse emission stemming from this part of the map. And then again, we can start playing with this emission, trying to see if it's related to these pulsars or something else. And just looking again to this particular guide, that is 1908, we just didn't not only look at the large emission around it, but what we tried to do is to see if we could see different emission regions, trying to understand, because this is one of these unidentified sources that has been identified for longer, despite the deep multi-wavelength observations and the all information we have about it, but still we don't know what's powering the TV source. And what we try to do is to look at the energy dependent morphology, again using the field of view background maker and ring background maker, and also gamma 3, gamma pi. This is the two maps, a combination of two maps, in red above 10 TeV and in blue below 0.6 TeV, to distinguish these two regions that seems to appear. That's kind of a softer region, and this high energy emission around here. But I should just say here that this is like a hint or an indication, but still we don't see anything really strong differentiated, so we can really claim there is an energy dependent morphology. But basically we can see also there's some emission coming from this supernova here, and we can just plot the spectrum of the whole region. This is Fermi-Lat. This is again the points from the LASSO paper. This is the Hoax point in green, and H.E.S. is with H.E.S. we get all these points here. So there is that basically give us a very nice sampling of the source from basically hundreds, 1 GeV to hundreds of DE, which surely help to try to understand what's going on. And this difference here, I think we kind of understand that by looking at this very diffuse emission which is integrated. So continue with these large sources, I just want to say a couple of things about electron factories, and this is like typical pulsar with nebulae, and pulsars which are injecting electrons in the interstellar medium, and then they produce this huge pulsar with nebulae that we see very bright in TV through inverse quantum. One of the interesting guys is Geminga. Geminga is very close by, and it's like 250 parsecs and it's pretty old. And it was claimed by it was observed by Hoax with a very large emission region of up to 5.5 degrees. So with H.E.S., we try to look at it. We know it's a very large, and it's basically a bit out of our range, but we still thought we can just look at it and see if there is any substructure that we can actually investigate. And you can see that also like the surface luminosity is pretty low for this guy. So this is the significance we get with plot versus the integration region radius, and then we see that the emission goes up to 2 degrees, which is the maximum we can actually look at, and still it seems like it's continuous. So we can really verify that this is at least 2.3, 2.5 degree radius, and it's still significant at this energy as Hoax saw. Something else that we are looking at is it seems to be an anisotropy in the emission. This is we distinguish two regions. We call it A and B, and then we looked at the signal here, and it's clearly detected the luminosity of the A region is 1.5 times the luminosity of the B. So that's more details. Again, you can look in Alison's contribution at the ICRC, and this is something we're still preparing the paper, and that will be coming up soon. And also, if you talk about cosmic rays electrons, we can talk about cosmic rays factories. We can talk about cosmic rays factories, and then of course one would think about open clusters. As you remember, Fermi labs have seen many of these kind of large bubbles around position of active stellar formation. This is the bubble around Westerlund 1. This is Westerlund 2 here, and then there's a large bubble 2 degrees here. This is also Cygnus or the Cygnus cocoon, and here in the Celtibrados. And they all seems to have a similar spectrum that extends towards high energy. So we indeed try to look at the skies. In the case of Westerlund 2, that was detected previously, and then we see like a compact TV source 0.2 degree around the cluster. And then regarding Westerlund 1, we had a deep program, program to observe deeply this source, trying to say something about it. This you can find it now also in large contribution at the ICRC. And this is the first preliminary maps we are getting. And then what we see, indeed, of course, this source belongs somewhere else, but this is what we see. This is the position of Westerlund 1. And then we see this very complex morphology. It seems to be a kind of a dip in the surrounding of Westerlund 1. And then you have this kind of two hot spots and then some bright part here. We also look at the EV, it looks compatible results looking by that. And something interesting that we see is that the spectrum seems to be, well, it's like around 1 degree, which means it's 70 parsecs at around 4 kiloparsecs. And we see there is no radial there's no change on energy in all this. We look at the normalized H.E.S.S and the radial profile, and the radial profile seems similar at different energy bands. So we don't see energy dependent morphology. And we don't see any change. We look at the spectrum at different parts of the map, looking at small regions within the emission region, and it's all these lines here. They're all compatible with the same kind of spectral energy distribution. So we just add everything together, and this is the spectrum we get now. And if you just use like pion decay scenario, then you end up with well, I like to just emphasize that we have, again, this goes up to 100 TeV, and then we have a cutoff in the protons around 400 or 400 TeV. This is the kind of spectrum you could feed if you assume an exponential cutoff power law in protons. And then you have this, this is the kind of energetics we derive by assuming a density of the media of 10 centimeters cubed and a distance 3.9 per-parsec. So we're working on this, and we're trying to understand what, how to interpret this in terms of radiation. And of course, this paper again is in preparation. It will be published soon. And finally, regarding these large cosmic rays factories catching, I just want to mention something that was also presented at the ICRC. This is just another things that we are trying to look is into these very large molecular clouds that it kind of catch cosmic rays, and then they illuminate. They are illuminated, and then we should be able to detect it in TV just by proton-proton interaction. So we have a number of them. This is one of the most promising one, this cloud 877. And we selected because you see that there was an excess in LAT and the hard spectrum. And indeed, we used this again, this 3D gamma pi field of view background, and we used the template by dust to try to. This is the contours of the dust map. And then what we saw is that we have indeed more than 6 sigma. We detect TV emission coming from this very region. And then we can just derive the spectrum. This is again the 3 points for H.E.S.S, then in red. And we see that here, if you compare to the cosmic ray density, the mean density in the galaxy, we get 5 or 6 times more cosmic rays than the local one. And also the spectrum seems to be harder. So it must be something like either there is some reacceleration of cosmic rays in this cloud, or there must be, or there is another accelerator, another source which we don't see here. So I just move now to a bit of galactic sources. I don't want to finish without saying a couple of words about Pulsar nebulae and Supernova Remnants, which are in the end, as you see here, they are the most numerous known sources in the TV, in our TV sky. But it's, well, not really true. The most numerous are actually these unidentified sources. There is a lot of work still to do to try to identify the skies. We are at the order of 60, 70 unidentified sources. And now if you look at here, we have a number of binary sources, which are also very interesting objects. We're still working on them, even if I'm not covering in this talk. But then we have some new source class that I'd like to briefly discuss, which are basically pulsars and NOVI. So regarding this pulsar nebula population, I think we are kind of completing the whole picture of what do we believe is pulsar nebula work. In general, you have this kind of stage 1, in which the pulsar is still within the influence of the shock of the supernova remnant. And then we have we still have many of these interesting objects. There's still a lot of data actually from the archive that we still need to look at it. This is one guy is 1119. This is within this supernova remnant 292. We have there is also a non-thermal X-ray, a radio counterpart of the Plerion, and something very interesting about this guy is that is related to a pulsar which has a very large magnetic field, 4 10 to the 13th, and is identified with a magnetar behavior. So this could be kind of interesting understanding how magnetar could also produce a kind of typical pulsar nebula, TV pulsar nebula. Then we have this kind of stage 2, which is like basically the remnant is very diffuse around, and then you have this kind of very large pulsar nebulae, which lasts for many years. And one of the best prototypes, because it's very large and it's very bright, is 1825. And of course, we are revisiting this guy. We have a couple of a new paper a couple of years ago. And we can just get our very good energy dependent morphology. We also identify this guy here, 1826, as a new source independent of this, and something. And now we can look at different energy bands. This is less than 1 TeV, and then you go here to higher energies again, and then something. There's a couple of things very interesting. For instance, that we see the emission is not at the pulsar itself, but a bit offset, and then we also look at the radial profile, different regions, and trying to see, really see, can distinguish between advection or convection transport of particles. Just want to let you know that this, if you look at this guy, this is this famous gamma ray binary 1539, which is in the field of view. Just gonna give you some hint of the still very TV emission around above 10 TeV, which makes it very interesting. And then again, if you compare, now we get the spectrum from LAT. This is from 100 MeV. This is the TV. H.E.S.S data, and then we again can join with LASSO, and then we have a fantastic sample of the spectrum from 100 MeV basically to hundreds of even PeV. So this is really something fantastic that we can start working with in the next months. Regarding the remnants, the remnants is still there, they're still bright. I found this thing interesting. This is all a compilation of all these remnants for which we know we have historical record of the explosion, and now all of them, they basically been identified as a TV detectors. We have, of course, CDY-86, and in the sky we look, we have more data, now we see clearly a shell-like morphology. You will remember Supernova 1006, in which you see this kind of bipolar mimicking this the non-thermal emission too. 1713, of course, and recently at the ICRC we also announced that the hint around 4.6 sigma of Kepler, which is the last supernova that was missing in this compilation, to be proven to be emitting TeV. And just to be complete, I just put here, this is C358, which is kind of Clarion-like crab, but then we have CAS-A that was detected by MAGIC and Veritas in the north, and also Tijo that was detected by Veritas. So the whole thing has been we can just say, okay, all the supernova remnants that we know that they're young, and they are TV emitters, and we look at but when you look at the differential luminosity versus energy, what we actually see is many of them, it seems to have a break or in the spectrum at around a few TV. So the question is still out there, like it is clear the TV, I mean, the supernova remnants are contributing for the cosmic ray C, but still unclear what's the contribution in the PV regime, in my opinion. Then I just finishing with these two last new kids on the block, as I said before, and I call it phase dependent in a sense. So one is pulsars, because you get this light curve, which has the periodicity, they're pulsating, and we with CTA, with CT5, especially with a very low energy threshold, we put a big program to look at pulsars. And Vila was actually detected in 2018 after 40 hours of observation, only with CT5. And this is the light curve here. This is Fermi in the lower panel. This is above 10 GeV, and this is about, the clear one is about 20 TeV multiplied by 3. So this is just to show that we see this P1 is decreasing and you don't see them anymore as you go high in energies, while P1 becomes P2 becomes more prominent. And what we see in H.E.S.S is basically we don't see anything in P1, and then we see this P2. And this is the spectrum we measure in H.E.S.S. So basically we could say that this is not a super exponential cutoff or exponential cutoff, but basically we measure something like a sub exponential cutoff. And that's not the end of the story. We continued observing, not just with CT5, but the rest of CT5, but the rest of the array. And we actually saw the P2 popping up above 3 TeV. This is again the flat light curve, and this is what we see above 3 TeV. And now we have a clear detection actually up to 20 TeV with very hard spectrum, which shows that we have a new component over there. That's not the only pulsar we detect. We also saw 1706. This guy, we're still looking at it. We have, this is a preliminary results from the first data we took, in which we got very good agreement with what Fermi sees. So we are confident about our light curve and analysis tool, and now we have 60 hours more on the pipeline to look at it, not just on to understand the shape of the end of the high energy emission and the beginning of the TV emission, to see if we see something there. I just want to finish with saying a couple of words on NOVI. And NOVI, they were a surprise. It was a surprise detected in LAT for many years, and H.E.S., in H.E.S. we had a program to follow the most promising one, basically LAT detections, LAT fast shock velocity. And last August we followed this NOVA, this trigger that happened in RS of Yuki in the 8th of August, and then we basically detect a very prominent signal which lasted almost 1 month. And just to give you like relevant of the community, there was a lot of interest. We had I counted more than 30 astronomical telescopes in less than 2 months. And we actually issued two telegrams, H.E.S. detection of the detection of the NOVI. That was a couple of days after the NOVA went off, and then we also provided information about the spectral that we were measuring. That is pretty soft, and this is something that it is of course now in press, and we hope to be able to share with you soon. And I get to my conclusions. I hope I'm not too far, not overdid my time too much. I hope I convince you that we still have a great instrument. We just do not only in the sense of hardware, but also software. And then we are getting really exciting new results. And we still continue observing our galaxy and obtaining high quality TV information. And I just want to end saying, like, the experiments has been extended for 2 years more by the steering committee. That means we have 2 years more observation minimum. And during that time, we want to do, we're moving into what we call the legacy observation program. So we basically identify observations that H.E.S. can still say something before the advent of CDA, and give some relevant information to community. And so, of course, we have a lot of transients in this program, but we have a lot of observations on many of these galactic sources I just discussed. Yeah, so we are happy also to get people on board if you have great ideas. And thank you.
Thank you, Emma. Thank you for the excellent talk, and thanks for the great summary. Can I quickly ask for the H.E.S. plans for future observations? You said that H.E.S. has been extended for 2 more years for legacy. Is it? I mean, do you think that will probably continue for beyond that during the time that CTA is running as well?
Yeah, I mean,
because I think right before CTA is producing results, and
yeah, I think it's just always a question. I think everyone is keen of continuing with H.E.S. Everyone wants the instrument to continue working because it's really in good shape. And it's not just a question of H.E.S. can do this or not. It's a question of is there enough human resources to run H.E.S. while building CDI. So, and this is here the problem. I don't think it's about the scientific result, but more political. The big institutes are kind of pulling off because they have a lot of responsibility in CTA. We are trying actually to minimize the technical support of H.E.S. I think this is also done in Veritas for a while, if I understand correctly, to have very we basically do shifts remotely. We control. We're making everything very automatic, and if we manage to minimize the technical involvement of the institute, we still could just continue as a. But right now there is this 2 years, and then actually the plan is to not continue after 2 years.
Yeah, and you know, I mean, while I wait for questions from the audience, please, any questions, just raise your hand or put it in the chat. I just one more follow-up question. Are you thinking of a different observing strategy? Are you going to focus on some kinds of sources? I mean, obviously, you will keep your TOO. The NOVA results are really fantastic and exciting.
I mean, I mean, actually, the idea was more because before we had like everyone writes your proposal, and then we say, okay, this is my proposal. I want to look at this particular supernova or whatever. Then I want to get 20 hours, whatnot. So the idea now was, okay, what can we do in terms of astrophysical problem? And then we say, okay, we want to look at supernova in different evolutionary stage. And then we look at these 3 or 4 objects. So the idea is to put observations. As you said, we of course have the TOO program, which is what we call the transients. And that we actually modified a lot of the allocated time because we have now great results on DRBs and NOVI. So we had to revise a bit how much time we want to put on these guys. But we still have some chunk of money on fundamental things like, I don't know, look for actions in M82. There's some different programs that we are. They've been for almost 1.5 years. And it went like bottom up to the managing and then down again. And then I think by now we have a clear idea what we want to do.
Mm-hmm. Okay, thank you. There's a question from Jen. Please go ahead.
Emma, very nice talk. And that get my attention on this 1908 source. That was on the page 20. That's very interesting results. And actually before that page, you showed you have this kind of comparison with the Hawk. Yes, this one.
Yeah, sorry, it's going too fast. Oh.
Yeah, so go too fast.
Okay, wait a sec. I just go here.
So seems to me you guys tried very hard to enlarge the range you look into, and to do the comparison with Hawk. Seems to be once you get the region is big enough, and then you catch up the flux similar the previous one. Can you show that?
Yeah.
Yes, something that's just like that. I think it probably you should you already have. Can you go that one with the Galactic Plane?
No, I think you mean,
you mean
the H.E.S. Galactic Plane survey.
Yeah. That one.
You mean the general
comparison with? Yeah, this one. Right.
Okay.
You see, in this map, actually, you made this the range. You survey the range and very little bit larger than previous one, right? So that makes this range looks very close to what Hawk saw.
Yeah.
So, however, once you shoot that spectrum of 1908, they still have quite a bit of difference between the flux of measured by Hawk, then measured by H.E.S.
Yeah.
Do you use the same technology here to enlarge the range when you do the spectrum?
You mean here we still see like a deficit with the flux? Yeah, that's correct. And I in principle we're using the same region than the people from Hawk, but we still see a deficit in the spectrum, and that's.
I see.
And I mean, this is something we need to really understand. In my opinion, I think this is due to this part that is here, you know, all this part that is kind of contaminating or we are not actually integrating. So something that we need to do actually is to try to understand if we make a larger field view to see if we can actually reach this value. But indeed, if you look at here, it seems to be like here, the higher energies you see a very nice reaching with Hawk and Lasso, and then it goes a bit flat and then it goes a bit down. So we really need to understand if we somehow are not at missing the tails somehow from the mission. Yeah, but that's actually true.
Mhm. Okay,
So
thank
the
you.
integration region for this spectrum is the 0.4 degree. That's the enlarged in the H.E.S.S analysis.
It's even bigger than 0.4.
Mm-hmm.
I'd say it is the whole integration radius model is more into the 1 degree, 0.7 or so. So this is what we use here is 0.4 with that we used for to compare.
That's the H.E.S.S and the Hoax comparison.
Hoax, which is earlier, no? No, I'm going back. Sorry. This is just to compare because we thought, okay, 0.4 is more or less the BSF from Hoax, and then they did the comparison just to use similar integration radius.
Yeah. This mismatch in the spectrum is seen actually also for other sources, right?
Wow. Yeah, I think actually something else that I didn't discuss here because it's still a bit preliminary. It's like we're trying to understand our data at the very high energies.
Mm-hmm.
And if you want, you can also look at this here is to 1825, which is very bright. But then again, this is LASSO, this is H.E.S.S, and then we always seems to be missing some data here at the highest energy, and that could be basically because we don't have enough background sometimes to really understand what's going on.
Yeah,
and this is we are trying to optimize. We have like a task group trying to understand how can we improve this, and this is something that is really ongoing right now. Yeah,
very interesting. All right, we have a question from Pratik. Go ahead, Pratik.
Hi, Emma. Yeah,
Hi,
it was on the same line about what you just now discussed. I think it's not just the extension region, but also the fact that at very high energies, you are source statistics limited.
Yeah.
So, and at the same time, probably in the other case, in the air shower array cases, I do not know. Can you comment how good are the background rejection at these energies in the air shower array cases? Because you are going down to lower energies for the air shower cases, like at 20 TeV, 30 TeV kind of cases. How good is the background suppression there? It could also be that a large number of hadrons are estimated as gammas, identified as gammas there.
If I understand correctly, basically there is no background, but they probably Chen can answer better than me, but there's very little background.
There should be some background for the air shower array cases, not for ISCTs.
No. This is not the case. In this region, actually, the rejection is still very good. Something around the 10 to minus 5, 10 to minus 4.
I see. Okay.
All right.
Okay. Thanks for that. Okay.
So I have a quick question here about the full width half maximum. Emma, is the angular resolution of 0.05 degrees defined as full width half maximum? What is that is the definition, right?
Yeah.
Okay. All right.
Well, it's not like exactly like this because you know, like the PSF has got like a kind of tails. It's not just like one single Gaussian, but yeah, that's basically. Yeah.
Okay. There's a question from Ruo. Go ahead.
Hi, Emma. Thanks for this great talk. I also have a question on Lighting 08. So from this, you show this energy dependent morphology of Lighting 08. Could you go to that page? Maybe there's some delay in my.
I mean, here in 20, slide number 20.
Yeah, this one. Yeah. So do I understand correctly that this low energy, I mean this blue region, it also covers this region B, or it's just concentrate on this region A?
It covers also region B.
Okay.
If you go another.
So for
the thing
this,
is, yes, I mean this we should take it a bit with careful because we cannot really see that there is a rhythm. We see kind of a 3 sigma effect but we cannot really say this is really, it's not as clear like what you see in 1805, between 1825 or, 3003. It is not, it seems to be, I mean, if you want to put it like that, it seems to be hard, the high energy seems to be coming from the century, from the B region, but still the bulk of the emission also comes from the whole.
Okay.
I think it's a bit like the same like we saw with Fermi, remember? Like we see very compatible morphology with the LAT. At the
Yes. Okay, thanks. And I also have a quick question on this Jaminga's halo. So what is the energy range measured by H.E.S.S? I mean, for the asymmetric morphology, what is the energy range?
Well, I cannot tell you exactly because I don't have it on the top of my head. I don't think there was like a particular energy dependence investigation because, as I said, the surface brightness of these guys is very low. And I would say out of my mind that this is all the data we have, so above threshold. But I think it's better if you just go to Alison's proceeding and see. But I would say this is just about threshold, like around 100, 200. Well, Jaminga is pretty low, so it should be like pretty high threshold.
And also from this right panel, we see the significance continue increases with the integration radius. So does it mean if you further increase it beyond 2 degrees, it will go further up?
Yeah, that means exactly this, that we basically, we don't, the whole emission goes on top of on our field of view, and we cannot just, I mean, what we could try to do is we can try to continue sampling around and make it bigger and bigger, but somehow one has to think what I tried to say before is like, what's the strength or weakness now? I mean, I think our strength is not to try to get the 5.5 degree source because it's way too high, too large for us. It's like trying to look from a Fermi lat. But we could do is to look at these small regions and see if we can see any. If that's confirmed, this change, asymmetric, it's very interesting because that would mean we have different diffusion coefficient depending on the pulsar proper motion or whatnot. Or
yeah. And is it able to do any energy dependent morphology here? Is it sufficient statistics sufficient to do such kind of study?
No, I don't think so.
Okay.
I don't think we can do that.
I see. Okay. Thank you very much.
Okay. But I mean, something interesting. We're looking for more halos. So now that we have the technique, we kind of trying to look for more halos.
That's
I mean,
great.
The thing is with the Jaminga is very close by. That's why it's so large. But we can also without just look at some kind of Jaminga source. Jaminga-like source is a bit far away, so we can actually still resolve it, but within our field of view. And we have a couple of interesting results on the pipeline. These guys.
That's great.
Other questions? I have a question actually. Before maybe this is a question for the theorists in the audience. You know, the source that you showed at the very beginning, the H.E.S.S J1702, I think, minus 420, the first source, where you resolved it into two different sources. And then the spectrum is completely different. I mean, this gamma 1.5, how do you explain that? That's extremely hard, right? And it's a very well measured spectrum.
Yeah.
How many hours of data is this?
I mean, I don't know on top of my head, but it's a lot of hours.
100 plus.
Yeah.
100 plus. But how do you explain the 1.5 hard spectrum? This is, I don't know.
Did we started start discussion?
Yes. There's a question by Paulo. Maybe Paulo, is your question related to the talk, or we should come back to the discussion?
It was related to the talk about.
Yeah, go ahead.
1908, when in that right-hand plot before, you were talking about the significance increase in different ways. Is that an estimate of what the systematics are now for the background? One was labeled FOV background, the other was subtraction, on-off subtraction. Because I'm wondering, watching all these talks, besides the field of view, the background subtraction is like critical. Like in Fermi, you can completely change the results. So to what extent is background subtraction an issue here? And could that also be part of what's going on between the two instruments? It's supposed to be background free, but it's not clearly, I guess, in at least in the one, it was at 1908. Sorry, it was the Gaminga halo, I think.
Yeah, I would say rather than, yeah, you know, I know you mean this.
Sorry, I got the wrong plot.
Yeah, no, in Gaminga, the difference between field of view and
yeah, exactly. Yeah.
Yeah, definitely in this case, and this is just statistic, and then you have to put the systematics on top. I think it's more not like about the background. It's more about how much you integrate. What is the contamination of photons around it? In the case of 1908, I was thinking. In 1908, I think the main problem is contamination for the diffuse emission around. Mm-hmm. In the case of Gaminga, indeed, there is a problem or a difference because of the background estimation, and this is because, as it showed in this plot, the emission continues beyond the 2 degree that we can see. So basically, if we use this ring background maker, we basically cannot use because we have a lot of background in the field, so there's nothing we can use. If we use on-off, you just look at somewhere else, and then there is a lot of systematic, as you all know, but using just like a background. This field of view background maker seems to be working better than the on-off. But Gaminga is a complicated field for us, basically because we cannot compare with the traditional field. I mean, the ring background maker is pretty stable, and we have also something like adaptative ring background maker, reflective background maker. So whenever the source is within the, I don't think we have the same problem from labs, because whenever the source is within the camera field of view and it's isolated and we can get background, then we can get a good estimation of the background.
Mm.
But whenever you have this very, very large emission, this is really, really tricky. And I'm not even talking about systematics.
Yeah, okay.
I mean, to get the spectrum, for instance, there we're struggling to get a really understanding of the spectrum.
Yeah, because from a theorist point of view, we're seeing different spectra that don't match up, and they have breaks or not breaks. So it would be nice to know if we tried to fit something, what exactly we should be fitting. Because you'll like if you compare lasso to this spectrum, you'll get different constraints on breaks and things like that. It's so it'll matter at some point. So it'd be nice to know. Or it looks like a high priority to make everybody agree and understand what region you're matching.
Yeah.
Okay, maybe one other question I want to ask. So like 2 years ago, there was some comparison between H.E.S. and Hoax, and there were a lot of Hoax sources that weren't reproduced in H.E.S. Is that gotten better now that you use 0.4 degree background, or is it still?
Yeah. This has been. You can actually look at this paper here, the H.E.S. and Hoax paper, and everything. You see, this is. I mean, everything is basically reproduced, and in that paper, actually, we look at different and specific part of the sky and compare 1 to 1. So everything else is basically. The conclusion is that we're looking at the same things, and we can trust some of the diffuse emission that we saw in H.E.S., even things like this, for instance. Then you see how all this kind of emission, this is the one that we saw in 1908, this is 40, but then you see all this diffuse emission is something that I think we understand now what's going on. But basically, there is a very good agreement between the two surveys.
Great, thanks.
Okay, Felix, we had a little bit of a longer discussion, but I guess we should move into the discussion section. You had a question.
No, I just want to discuss.
Okay, good.
Well, I think one thing, just a few comments. I think we should not exaggerate these differences at this stage between Hoax and H.E.S.S and LHAASO. First point is H.E.S.S, as Emma mentioned, is getting closer to Hoax. I mean, this conflict is getting less and less. Still, there's some tension, but I think with time it could be solved. So I don't think there's something mystical in that case. So I'd wait a bit. And H.E.S.S is doing, as Emma said, there's a lot of progress in understanding of the background. So this is my guess. I mean, soon will be good agreement. Maybe Hoax is not now very critical at this moment, but LHAASO is critical because LHAASO is giving, I mean, we are getting higher quality data and going to high energy. So in that sense, even we are at different, I mean, north and south, but we have a lot of sources, and first priority sources, actually exciting sources, which we have overlap, very good overlap, like good ones like 1825, 1908, there are more. So I think it's going to be a lot of exciting things in this regard. And what is good that H.E.S.S is now going to high and high energies, which is one of the greatest stuff from his recent results. We are going well beyond 10 TeV, and the LHAASO has a very nice sensitivity, already 30 TeV, so there'll be even good overlap, real overlap. I mean, I'm not, maybe at 100 TeV will be not so relevant, but even at 30 TeV, we are approaching to the both points. I mean, H.E.S.S is approaching, but LHAASO already had this point. So I guess a lot of exciting things are going to happen. So that I think we need a lot of coordination. It's true also for Magic and Veritas, of course, but even for Magic and Veritas, that is trivial. Both are in the Northern Hemisphere, but even from the Southern Hemisphere, we have a lot of coverage. So second point, what I want to indicate when going to highest energies, I mean, we have to, actually, I didn't expect that Emma will show this 1825, but since she showed that, let me comment on that. I mean, that is nice thing. She has a right to show, actually, as a convener. So yeah,
but that's the paper. That's the paper we published in 2018.
It's from the paper. I thought this is a bit different, yeah. But we are getting. I mean, I expect much more exciting results, in my view, from the source. But what I want to say, I mean, we should discuss different things. I mean, there could be not just one source. It could be just one source. When you are talking about two sources, like, could you show that 1702, Emma? I mean, that is the. Look at what is happening there. I mean, in 1702, you have this hard spectrum is a point-like source, is a very compact source, and that could happen. That is the same source. You see that the highest energies are. Well, I mean, we mentioned why you just removed that, Emma.
She didn't. I think we're trying to make it full screen, right?
Yeah, I was trying because I don't know how big can you see.
It's okay.
I think it's okay. I think it's relatively okay. So it could be just low energies are having this diffusively, or could just producing this the halo type emission, while highest energies are, I mean, we mentioned that already a few times, that It could be we are closer to ballistic regime. So even you are getting higher, larger and larger region, physically larger, I mean, like, but angular size getting smaller because of the, well, actually for this source, we have calculations now, I can tell you, it's not collaboration, it's private results, and we nicely could explain the point like source, the hard one and the diffuse one, like this one. Okay, nicely, because we know we want to fit, maybe it's not the case, but I just want to say the same could be case 1825. So you could see there's a the core at highest energies is very compact, and you see the diffuse emission, and that could be the same story. So what is I see exciting in H.E.S results, but we desperately need also the higher energies like LHAASO detected above 100 keV. It's all we are talking about Geminga. I mean, personally, I'm not very excited by Geminga in the sense because it's so big, it's so difficult. But we have a lot of other halos, and for example, 1825 is ignored. That is a classical halo, in fact. I mean, could be. And then we have a much larger size, and SARS is about 100 parsec. It cannot be possibly nebulae. I mean, it should be the halo. So that's just what I want to say, that there are a lot of things are coming soon. And then I expect everything will be okay. We have agreement with LHAASO and H.E.S, and the same LHAASO and Veritas Magic. And so we have to look at the things a bit non-standard way, just not, I mean, just taking all data. It could be in different ways, it could be compared. So this is the spectrum for 1825, right, Emma? This one is,
yes.
So it's, you could see there's not so bad, I mean, agreement, in fact, there, and it could be even improved. So I would not exaggerate these differences. It will be very important just to combine analysis. And then, of course, has advantages, or Magic Veritas advantages, angular resolution, perfect angular resolution, and for LHAASO is highest energies with still very good angular resolution, maybe not as good as H.E.S, but still good angular resolution. So it's, I guess a lot of things will come in next couple of years.
Yeah. Yeah, it's exciting times. Jen, you have a question. You want to comment?
Yeah, the Phoenix actually bring my attention to that 1708 or 04 or something.
1702.
1702, yeah, please go that. I have a simple question about this location. So this seems to be the declination is only -4 degrees. Is that right? The declination of this source?
The declination of the sky
is only a -4?
Yeah, it
No,
it's,
no,
it's very south.
It's very
south, -40.
-40?
No,
Okay.
No, it's
-4, I think. Let me see.
I think it's -4 degrees, right? If it is case, that should be in the field of view of LHAASO as well.
Yeah. It is -40, 1702, 42.
Yeah, it's very south. It's one of these kangaroo sources.
Okay. Then that's,
no,
I
unfortunately,
mean,
not LHAASO.
No, I don't think it's all this 17 part is really low.
This is a very interesting source. Yeah.
So Jules is asking if the source was checked for variability. Is it variable? I mean,
you mean this the point source?
Yeah,
we did check
the hot spectrum.
Yeah, we did check for variability and we didn't find anything. Flux stable within the statistics we have.
By the way, if you have 100 TeV gamma rays, if it's inverse Compton or pi zero, doesn't matter. You need 1 PV, close to 1 PV, at least 500 TeV electrons or protons. And in that case, if you take diffusion coefficient even 10 times smaller, you should get point-like source. These particles could not move diffusively. It should be ballistically first significant part of. So to having point-like sources at very, very high energies, 100 TeV, it should not be a surprise.
Do you think this energy is high enough, Felix, to be a ballistic? You're talking about something just like 100 TeV source, the photons, right?
No, but then is you have 500 TeV. If protons, then you have actually, it's hard spectrum. You have about 2 PeV protons for hard spectra. You know, for steep spectra, difference is factor of 3 or 4. But for hard spectra, difference factor of 20. So you multiply 100 TeV to 20 is about 2 PeV. Yes, I mean, that was, they should move very rectilinearly. So unless you assume very, very, very small diffusion coefficient.
But many of the sources from LASSO are large, no? Or do we see a lot of point source in the LASSO? LASSO would be perfect to test that.
Pretty much, yeah. Most of them are extended.
No, but question is, if it's extended also above 100 TeV or 200 TeV for gamma rays.
That's another question. Yeah. I agree.
So typically, for published LASSO results, statistic was sufficient to give above 20 TeV or 30 TeV. So question is, if you go to 200 TeV, maybe it could be different situation.
Yeah, certainly the statistics at the moment is not enough to make this kind of judgment. I agree, we'll have this kind of, the morphology certainly is a function of energy.
Yeah. Well, for electrons, you expect also because of losses, but protons certainly not. You expect something different, right? So higher, larger, if it's diffusive, if diffusion. So now about the question, if we are here, I mean, we are discussing also Stefan Wagner, maybe you could find out to have a meeting. I guess you have already memorandum with Veritas, but we don't have memorandum, I mean, with H.E.S.S, but without even memorandum, maybe you could find some sources to analyze together.
Sure, yeah, that would be very interesting. The reason we don't have just because we are the one in the south and another in the north, so we don't expect we have a very much overlap in the sky.
There are a lot.
But actually, we have this 1908, at least. That's very
there
interesting.
Many. There are much more.
Yes, I agree.
We have all this W43 part. This is
1809. We have 1809. So actually, exactly. Emma sent me some figure a while ago about overlap. I was myself surprised to see at least 5, 6 sources.
Sure.
I think there are some sources that we can observe, at large zenith angles and low declination.
But especially we are talking about the high energy part, right?
Yes.
Yeah. Sure, this is something really interesting to do. Yes.
Yeah, we can share those and see. I think there's some of them that are really interesting to compare.
All right. Another advantage is that actually we have some H.E.S.S members actually still in our collaboration, like Reizi, right?
No anymore.
He's not. Oh, okay. We don't have any.
Ruiz was, I think Ruiz was last one, but that was over. Yeah, but we could just organize it.
Sure.
We'll find a way to do all these discussions.
Anyway, once we have this kind of overlapping members in both collaboration, that's an easy way to do the collaboration. Actually, we can do the work first before we sign any this kind of MOU stuff, right?
Exactly, source by source, I mean, basis.
Exactly, yeah.
I mentioned that because for Veritas and Magic, it's so obvious, but a lot of people didn't realize that we have also very good overlap. And
Yeah,
look
look at what the Ima showed. This overlapping with Hawk. You know, Hawk just 10 degrees more
absolutely.
southern than Nozzle, right?
Yeah, exactly. I think all these parts we are overlapping with all this region. Yeah, I'll send you some, or Felix can share with you what we discussed a while ago.
No, better you share, not me. Because
You can blame me.
I cannot do that simultaneously. No, but we could organize. I talked actually, Stefan, also, we could have some committee or some small group to identify sources and go source by source. I think it could be very effective. The memorandum is a bit bureaucratic procedure.
Sure.
It could go faster.
I think that's a great idea. We should find something to work on together.
Sure.
Felix, we are at 10:30 New York, which is the end of the session.
Yes.
I think we should, Emma's been talking for an hour and 30 minutes. So thank you so much. It was really great.
Thank
and
you.
I also want to remind people that the next meeting will be on December 15th. And the talk will be by Andrei Baikov on modeling of galactic pevatrons. So it'll be a theoretical, I guess, talk, which will be very interesting. So looking forward to that and hope everyone can join.
Okay.
And I think we will just end today's session. And in the US, I think we are in the Thanksgiving holidays. So happy Thanksgiving to people from the US. And everyone have a good rest of the week. Bye-bye.
Bye-bye.
Thanks.
Thank you.
Happy Thanksgiving.
Bye. Thanksgiving.
Thank you, Emma.
Thank you.
Thank you. Thank you. Bye-bye.